Hi guys, BuildZoid here, and today we're going to be doing a motherboard PCB breakdown of the ASUS Maximus 7 Gene. And you might be sitting there right now and thinking to yourself, BuildZoid, don't you have any more modern motherboards that you could do a PCB breakdown of, or like GPUs or something? You know, something actually relevant to people looking to purchase hardware these days. And my response to you is like, yeah, I could. I don't want to, for a couple reasons. One, I kind of want to do this as a warm-up PCB breakdown, so yeah, because I haven't done one in ages, and if I screw this one up, it doesn't really matter that much. Two, I'm kind of bored of modern hardware. Like, it's all very similar. There was a lot more creativity in the power delivery design of old motherboards compared to modern motherboards, because with modern motherboards, the VRM design basically comes down to buy the very high phase count VRM controller, slap a bunch of random power stages onto it, done. That's it. Like, there. Motherboard complete. You know, and like the highest level of creativity is like if your ASUS or MSI maybe is, or actually everybody does it now, so it's just kind of like, yeah, and sometimes if you can't get the high phase count controller or the high phase count controller costs too much, you just take your PWM signal and shove it into 2 power stages at the same time instead of just 1. Amazing. And to be fair, there's nothing wrong with this. In fact, I would suspect that like in the past, because of all of the VRM design creativity, there was a lot more motherboards with truly awful power delivery, but it does mean that modern hardware is just kind of boring to look at if, you know, like, because the thing about the PCB breakdowns is they're not reviews. I know most people treat them like reviews, but to me, they aren't reviews. They're about appreciating the components that go into making a motherboard. And so, yeah, like modern motherboards are kind of like, well, this is the same, like they're all very similar, and so they're kind of boring to take a look. So they're kind of boring to look at. Also, because people treat my PCB breakdowns like reviews, I do spend a lot of time sort of thinking about like how what I say about a motherboard in a PCB breakdown is going to affect people's purchasing decisions, which I really don't enjoy doing at all. Like, yeah. So doing an old irrelevant motherboard like this, I don't need to worry about affecting people's purchasing decisions because it's old and irrelevant and nobody's going to buy it anyway. So yeah, and you might be like, but why do you concern yourself with like people's purchasing decisions? I don't want to recommend a bad motherboard to people. I don't want to make I don't want to accidentally make a bad motherboard sound good. And occasionally I do. Because a lot of the time, like, getting a PCB breakdown done is, like, kind of a rush compared to doing all of the technical testing. And arguably, like, and the funny thing is, if you have all of the test results, you don't need the PCB breakdown, right? Like, the PCB breakdown really is more like, this is what makes the motherboard tick, not so much, this is what makes the motherboard good, right? Test results tell you if a motherboard is good or not. PCB breakdowns are more just about, like, I like looking at motherboards, and that's kind of it. Anyway, with that out of the way, let's take a look at this old board. After all, I spent a decent amount of time, you know, looking up all the component specs and calculating the VRM efficiency, so may as well at this point. So let's start off with the feature set. So Maximus 7 Gene, this was back in the days when you could get like a high-end MATX motherboard and high-end MATX motherboard, and the Gene was sort of the peak of that. And actually, with the X670, ASUS is bringing back the Gene name at a price tag that's like 3 times what it used to be. This board was apparently around $200 when it launched. So, yeah. Anyway, I mean, to be fair, compared to modern motherboards, this thing is very simple, especially since it's a Haswell-based motherboard, but anyway, yeah, let's go take a look around the feature set. So you've got a power button, reset button, these 2 buttons which do things not related to overclocking, so I don't care what they actually do. So yeah, those exist, but I don't know what they do because they're not overclocking related. There's a clear CMOS button in the rear I/O. There's also a ROG Connect button, which doubles as a BIOS flashback button, so you can update the BIOS of this motherboard even without a CPU installed. Potentially, if you screw up a BIOS flash, that button can, like BIOS flashback can still work, which is pretty neat. And there's also some other like the ROG Connect button had like a bunch of I'm not sure depending on which motherboard you have. I think for some of them it had like the option for like a I don't think this one does it. But there was some motherboards where you could have like an on-screen overlay for overclocking. I think on this one it might be overclocking via Bluetooth using a phone app, something like that. Like yeah, ASUS was experimenting with all kinds of wacky external overclocking controls with the ROG Connect button. These days, that's not really a thing on ASUS boards anymore. If it wasn't such a stupid gimmick, I would actually miss it. But like I've tried using the ROG Connect functionality on some of the boards that I have from back in the day, and it was it was the kind of thing where you tried it, it was like, oh, this is kind of neat, and then I never used it again because it was really not that convenient to set up. Anyway, speaking of BIOS flashing, the board has a single BIOS chip, but at least it's socketed. So if you somehow manage to really screw up, you could always just pull the chip right out of the board and replace it. Pull it out of the board and flash it with an external flasher. If that still didn't fix it, then you could just completely replace the BIOS chip. So that's pretty neat. Then up over here, we've got a bunch of voltage read points. Next to that, we've got a postcode, which is always extremely handy for, troubleshooting any kind of boot up issues. Man, remember when you could get a postcode on a $200 motherboard? That's not a thing anymore these days, which really sucks. Like the cheapest motherboards, actually no, that's not true. The B550 Steel Legend is under $200 and has a postcode. But yeah, it's a rare thing to have these days, which is really sad in my opinion. Anyway, below that we have an LN2 mode jumper. Now, on most actually you wouldn't get this on most ASUS boards. You get this on ROG boards. On most boards where you have an LN2 mode jumper, the main thing the jumper does is it removes a bunch of voltage safety restrictions. But the other thing it does on a lot of motherboards, not necessarily all of them, is it preloads a bunch of voltages for helping with cold bugs and cold boot bugs. And the thing about those preloaded voltages is they can be very, very high. So on some motherboards, this LN2 mode jumper is actually very dangerous to use if your CPU is at like ambient temperatures, because you're really meant to only like use this jumper once you're down at like minus 100 or lower. Now, I'm not sure if this motherboard does that, but there are definitely ASUS motherboards where that LN2 mode jumper, if you use it at on water cooling or air cooling, you can potentially damage your CPU with it very, very quickly. So yeah, there's a reason why it's called LN2 mode. I really wish it wasn't dual function though. Like I feel like it would have been better to have an over voltage jumper separate from like a cold bug removal jumper. But yeah. Anyway, next to that we have a MemOK button, which acts as a sort of partial clear CMOS, because the idea behind this is that it erases all of the settings that affect your memory stability, which also includes all of your CPU settings, because, a badly set up CPU overclock can cause memory instability, so that's what this is for. Not as helpful as a safe boot button, which came out, I think the first board that had a safe boot was the Rampage 5 Extreme. But, that doesn't hurt anything by existing, so a neat feature to have nonetheless. And that's kind of it in terms of overclocking features on the board. Yeah, the funny thing is, ASUS never really did the thing that a lot of other motherboard manufacturers did, where they would just hurl buttons at their overclocking boards, right? Like you'd have a ratio button, like CPU ratio up down button, BCLK up down button, profile buttons, all kind of just buttons for absolutely everything. Which personally, I'm a fan of that, but yeah, ASUS never really did that. And also, this is an MATX motherboard. There's really not that much space for a bunch of random extra buttons, but yeah, this isn't that different from what you'd get in terms of overclocking functionality on, say, like an Extreme or even a Formula. Back then, Apex boards weren't a thing yet, or an Impact, for that matter. Anyway, yeah, so that's the overclocking features, and now let's go take a look at the power delivery. And compared to modern motherboards, the power delivery on this board is extremely simple, which is kind of cool. Actually, even compared to old motherboards, the power delivery on this board is extremely simple because this is a Z97 board, so it's for Haswell and Devil's Canyon CPUs, which means that the VRM does one thing and one thing only. It outputs VCC in, and VCC in is then converted into all of the the actual like CPU level voltages by the CPU itself, because Haswell and Devil's Canyon CPUs have the fully integrated voltage regulator, which is basically a very, very, very high frequency, quite high, very high phase count. Actually, would it even count as multiple phases? Because I'm pretty sure they just had like separate volt. No, I think some of them were probably tied together for like. Yeah, so like you basically had a very high frequency, high phase count voltage regulator built directly into the CPU, which would take the VCC in voltage, which would nominally be 1.8 volts. Though if you're overclocking, you're likely to bump it up to like 2 volts or higher. Especially if you're on liquid nitrogen, you're likely to bump it up to 2 volts or higher. But anyway, it would take the VCC in voltage and it would convert it into Vcore. Actually, back then we also had an uncore voltage, which was kind of neat. So yeah, you'd have like so you'd have your core voltage, ring voltage, system agent voltage, I/O voltage, iGPU voltage, and all of these voltages would be generated on the CPU itself instead of by the motherboard, which drastically simplified the VRM design, which is kind of neat. And also, it also helped with the efficiency of the VRM because instead of, like, let's say you had a CPU that pulls 200 watts. Well, instead of shoving 200 amps into the CPU at close to 1 volt, you could now shove 100 amps at 2 volts into the CPU. And with VRMs, most of the power loss, or, okay, that's not, no, most of the power loss is related to the I squared R losses. And I squared R is your current squared times the resistance of your MOSFETs, as well as the resistance of the power plane and the resistance of the inductors and the socket, basically everything between here and the CPU itself. So if you pushing 200 amps into a CPU at 1 volt is way more difficult from a power in terms of achieving good efficiency than pushing 100 amps at 2 volts. Because the voltage itself doesn't really affect the efficiency that much. The current, on the other hand, is literally quadratic, right? If you double the current, your heat output potentially quadruples, or at least a big portion of your power losses gets 4 times bigger. So yeah, the fully integrated voltage regulator in many ways was just amazing for power delivery. There was one major downside with it, which is that it doesn't work at liquid nitrogen temperatures like at all. So Haswell CPUs and Devil's Canyon CPUs all basically stop functioning somewhere between like minus 150 and minus 120 degrees Celsius, which is really inconvenient because they clock higher the colder they are. So yeah, that's kind of the one downside to the fully integrated voltage regulator. But I'm really not sure why Intel stopped using it. As far as I know, they still probably use it on laptops, but yeah, I'm not sure why it stopped being so common. These days, it's mainly seen on like server CPUs from Intel, where just because server chips pull ridiculous amounts of current, it still makes a lot of sense to have a VCC in instead of having like 1 volt 400 amps. You have 2 volts 200 amps going into the CPU or something like that. But yeah, like I'm really not sure why they got rid of it for like regular desktop chips, but they did. Which is great for extreme overclocking. Actually, they didn't completely get rid of it. Z690, there's a VCC in for parts of the memory controller, and I think the L2 cache for the E-cores. Like there is a partial integrated voltage fully integrated voltage regulator on 12th gen. And I think there was actually for laptop CPUs it might be, I don't know. Yeah, so Intel's been really weird with like Haswell, it was like everything was handled by the fully integrated voltage regulator, and now the fully integrated voltage regulator handles parts of the CPU instead of all of the CPU, which, um, yeah. I wonder what the like specific reasoning for all of that is, because like from my perspective, I don't really get why they ditched the like VCC in goes in, Vcore, and the CPU handles everything else itself. Like I don't know why they ditched that design. Um, because I don't think the cold bug was the like I don't think Intel cares that much about LN2 overclocking that they would like harm regular use power delivery for the sake of LN2 overclocking. That doesn't make a ton of sense to me. But anyway, thanks to the fully integrated voltage regulator, the power delivery on Z97 and Z87 motherboards is very, very simple compared to what we have these days. Or even before Z87 and Z97. It also helps that the CPUs really didn't pull very much power. So let's talk about how this VRM is actually, like what this VRM is made up of. The controller is this chip over here, and that is an ASP 1257. So this is a rebranded ASUS part. I suspect it's an international rectifier chip just because, well, the board uses international rectifier driver ICs, and typically you will see the same manufacturer used for both the controller and the drivers. So since this is on a bunch of international rectifier drivers, this is probably an international rectifier controller. Unfortunately, I don't know who exactly makes the ASP 1257, but yeah, I would assume it's a rebranded international rectifier part. This is running in 8+0 phase mode. And this was one of the well, the funny thing about having an 8 phase for Haswell is it doesn't really do anything because all of the heavy lifting in terms of voltage regulation is handled by the internal voltage regulator of the CPU. So, which actually, like ASUS, I don't think ever did this, but there are motherboards from like ASRock and Gigabyte, which like really take advantage of the fact that the power delivery, and actually MSI, you can also see this on some MSI boards. With Z97, there's a lot of motherboards which have super basic power delivery designs on them because the integrated voltage regulator does everything. And so the motherboard, so there's like a Gigabyte overclocking board with like a 4-phase VRM because it's just like, well, we don't really need more than 4 phases when the CPU does all the heavy lifting. So, yeah, but ASUS, for whatever reason, didn't decide to do that. And so they stuck a full-on like 8+0 phase VRM on here. Like the thing is, it wouldn't really make sense to run the VRM as like a 4+0 or something. But if they made this a 6 phase, I don't think it would have really affected the VRM thermals in any way, shape, or form. So yeah, I'm not saying like, oh, it would have made sense to do something like this. That would be stupid. In fact, that would probably cost more rather than cost less. But I'm surprised that they didn't go with like a 6+0 or even a 4+0 because this is literally what Gigabyte did for one of their motherboards. And that was like an actual like overclocking focused motherboard. And they were just like, yeah, just make it a 4+0 because it's Haswell. It doesn't matter what you try to power it with. Anyway, 8+0 controller setup. For the drivers, we're looking at a bunch of international rectifier IR3553s. I mean, 3535s, not 3553s. 3553s are 40 amp power stages. These are 3535s. These are just drivers. So all these do is a PWM signal comes over from, where's the controller? It's right here, isn't it? Yeah. So the PWM signal comes over from the controller, goes into the 3535, and the 3535 connects to the the gates, and actually the switch node. Like it just connects to the MOSFETs and the inductor of that phase, and it actually drives them, right? So that's the chip that's actually switching the MOSFETs on and off. And also making sure that the two MOSFETs aren't turned on at the same time, which would be very bad, as that would be just a short circuit from 12 volts straight to ground. Yeah, anyway, so we've got 35s for driving on the back, and these are designed for switching frequencies from 200 kilohertz all the way up to 1 megahertz, or also known as 1,000 kilohertz, which is not a very, well, to be fair, like, even on modern VRMs, you really don't want to be running them above like 500 kilohertz switching frequency anyway. It's kind of like, funnily enough, on a lot of motherboards, the voltage regulator actually performs worse in terms of voltage regulation if you just crank the switching frequency up. It has something to do with how the control loops of most motherboards are set up. On a lot of GPUs, however, cranking the switching frequency actually significantly helps voltage regulation. So, yeah, interesting how that works. Anyway, since this is a Haswell board, I should have maybe tried to measure the switching frequency, but ultimately it doesn't really matter that much. Actually, if anything, I think if this board actually worked, like the thing is, I did buy a dead board, right? Like you can see the socket's completely trashed and the clips are broken, but or a clip is broken, but the thing is, with a board like this, and because of the Haswell integrated voltage regulator, I think it would probably be best to run this board at a very low switching frequency, because that should give you better VRM efficiency, and it wouldn't really affect the voltage regulation in any way, shape, or form. So, at least it shouldn't. So, yeah. Anyway, so that's the drivers that this board is using. And then for the actual MOSFETs, we've got Texas Instruments CSD 87350s, and these are up to 40 amp dual NFETs. So a dual NFET just means that we have a high side MOSFET and a low side MOSFET integrated into a single chip. This is like the one step before you get a DR-MOS component. A DR-MOS component is basically this, plus the chip on the back of the board integrated into one chip. Anyway, yeah, so we just have an integrated high side and low side MOSFET. And because these are specifically designed for like buck converter applications, Texas Instruments says that, hey, these can handle up to 40 amps. And theoretically, you should be able to, like, because these are basically just discrete MOSFETs, you should be able to actually just push more current through them, depending on exactly how you implement them, or a lot less, right? Like, if you put these on a 4-layer PCB and don't put a proper heatsink on them and screw up your, like, pad sizing, 40 amps might actually be pushing the limits of what your PCB design can handle. But anyway, that's not really a concern here. And one thing I do want to comment on before we get to the actual like power efficiency, like power losses of these MOSFETs in this VRM, is the actual layout of this VRM, right? Like you'll notice that there's an awful lot of space between like all of the phases, and they are actually all separate phases, right? There's no technically not separate phases because they share a PWM signal. Nah, these are straight up. Each of these is an individual phase. So yeah, there's a lot of space between the phases, and basically this is just a thermal optimization that you can do, which I'm kind of surprised to see, because again, this is Haswell. I think, like ASUS could have used half as much board space, and it probably wouldn't have affected the thermals of the VRM whatsoever. But the other thing is this board, as far as I can tell, is a 6-layer PCB. And like with a 6-layer PCB, you just kind of have the extra space to do, do things like this where, because like if you had a 4-layer PCB, having your VRM occupy this much space is actually potentially a problem for connecting things like USB ports and stuff to, say, the chipset. Right? So you'd actually potentially want this area of the board free so you have more space to run a bunch of I/O signals and that kind of thing. But since this is a 6-layer PCB, ASUS just kind of, and it's an MATX board, not like an ITX, ASUS does have the room to just kind of spread the VRM out to improve the thermals a bit. So, that's kind of neat to look at. This isn't really something you see a lot on most modern motherboards, because most modern motherboards is trying to cram as many power stages into a given amount of space as possible, which, to be fair, is actually better. Like, if you really need to handle a lot of current, having slightly better, thermal performance out of your up to 40 amp dual NFETs is just not as good as having twice as many dual NFETs, right? Like, if this had 16 of these chips instead of 8 of them, you'd have half the low side on resistance. Um, so, yeah, like, less MOSFET resistance is ultimately better than better MOSFET thermals. But if you don't need super low MOSFET on resistance, right, like, and you have the space, then yeah, this just helps the VRM run a bit cooler and doesn't really add any cost if if like it's not going to force you to add extra layers. Um, anyway, so yeah, so this is just kind of neat to see because there are other motherboards out there where there are other motherboards out there where this might have been an option, but the manufacturer just kind of slaps all the components right next to each other just because they kind of can't be bothered to do even minor like thermal optimizations like this. So I think it's kind of neat to see, even if it ultimately probably doesn't really matter very much. Anyway, let's talk about the heat dissipation. So, the documentation for the dual NFETs is unfortunately spec'd at 500 kilohertz, which is very high, in my opinion, for a motherboard that's like ultimately just powering Haswell CPUs. But it does have voltage scaling curves, so I've calculated the heat output for actually like 2 volts output voltage, which is a realistic voltage if you're doing like overclocking with Haswell or Devil's Canyon CPUs. Well, with Devil's Canyon CPUs, you might be using slightly less voltage, but with a lot of Haswell chips, they do benefit from a higher input like benefit quite a lot from having a high input voltage. And assuming 5 volts drive voltage, and there's really no reason to... Well, actually, on a lot of boards, ASUS does give you the option to adjust the drive voltage, but it's there's no reason to do that here. It's a Haswell board. You don't need that much current. Anyway, so outputting 80 amps of current, which, mind you, that's 160 watts of power going to the CPU, right? So that's a lot of power already. A 4790K has a stock TDP of like 88 watts or 95 watts, right? So already if you're overclocking, you hit 160 watts, which is quite a bit of power. And also, Haswell CPUs had thermal paste under the IHS, so if you didn't delid them, they ran really hot. Yeah, 80 amps, which, that's kind of like by today's motherboard standards, that's nothing. That would produce about 11 watts of heat, which should be absolutely no problem for this VRM to dissipate. In fact, thanks to the extra spacing between the phases, you could probably get away with this without even having a heatsink on the board. So yeah, like that's part of why it's nice that they spaced out the VRM so much. Anyway, at 120 amps, at which point we're pushing 240 watts into the CPU. And also, this is power losses only of the MOSFETs. This isn't accounting for power losses in the inductors or the power plane. But again, this is a 6-layer PCB. 80 amps is kind of nothing. Like, for comparison, on modern 6-layer motherboards, you can have, like, say, a 10th gen Intel or a 11th gen Intel CPU, or even a 9th gen Intel CPU. Those chips will be pulling, like, close to 200 amps when overclocked. So 80 amps on a 6-layer board, nothing. Kind of nothing. Yeah, so the fully integrated, like from a power delivery perspective on the motherboard end of things, the fully integrated voltage regulator was so convenient. Anyway, 120 amps, about 17 watts of heat from the MOSFETs. And yeah, this is still like this is like a stock 12900K. Actually, this is like less than a stock 12900K. So, yeah, like Haswell was very, very easy on the power delivery. There's a reason there was a bunch of high-end overclocking boards with just drastically simplified power delivery designs. Like this is quite fancy, to be completely honest, by Haswell motherboard standards. Anyway, let's crank it up to 200 amps. And, this is like the territory where most motherboards these days have to operate at. And, yeah, at that point, this VRM stops looking so impressive. Because 17 watts, at that point, you do need a heatsink, but it's not going to be, like, super difficult to deal with. However, 200 amps out of this VRM would produce about 35 watts of heat. Now, admittedly, this is at 2 volts. But the thing is, if you were pushing 200 amps through this VRM at 1.2 volts... it would still produce over 30 watts of heat, right? That's the thing, is like, the heat output really wouldn't change very much if you were at 1.2 volts compared to 2 volts. So that's kind of the thing. And so on a Haswell CPU, you're never going to hit this, right? Because that would be 400 watts of CPU power consumption, and Haswell quad cores just don't do that. That's just not a thing. Even on liquid nitrogen, they don't pull 400 watts. But especially because people don't run Prime 95 small FFTs on liquid nitrogen, but, you know, yeah. So that's kind of the thing, is just Haswell motherboard. Like, honestly, Haswell motherboards are probably the reason why VRM designs got really bad. Because for, like, with X79, the VRM design was extremely difficult. Like, designing a VRM that didn't run insanely hot was hard. With Z68, Z68, you still had CPUs that were pulling quite a lot of power, because even a quad core Sandy Bridge could pull over 200 watts of power quite easily. And it wouldn't be at 2 volts. It'd be at like 1.4, 1.5 or something. So, you know, you still needed a pretty substantial VRM. And then we got to Haswell, and it's like, you can shove this through a 4-phase. I mean, the 4-phase won't be particularly thrilled about it, but it'll work. And this is a lot of power for a Haswell CPU, right? Because, again, 120 amps, but at 2 volts. And so with Haswell boards, the motherboard manufacturers basically had the excuse to get really lazy with the power delivery. And then with Z170, things didn't really change, because 14 nanometer quad cores, sure, they didn't have the integrated voltage regulator anymore, but they were on 14 nanometer. They pulled even less power than Haswell did. And, you know, and then Intel kind of got stuck on 14 nanometer, and the core count started to go up while the per core efficiency didn't change for years, which is how we eventually ended up with like 10 core and 8 core CPUs that pull 200 amps, and, you know, suddenly the VRM runs very, very hot, or even over 200 amps in some cases. So, yeah, anyway, so this VRM is basically overkill for, you know, the kinds of CPUs that you could put into the socket, even though by today's motherboard standards, this is kind of a joke. And actually, if you compare it to some older motherboard designs, it's also kind of a joke. Yeah, like, Haswell was kind of cool in that the motherboard power delivery could be really unimpressive. Now then, let's talk about filtering configuration. Interestingly enough, this board has surprisingly low inductance inductors, which I find really surprising, because a lot of older motherboards would have very high inductance inductors, like a lot of, say, LGA 1155 motherboards, so like Sandy Bridge motherboards, you'd have like 400 to 800 nanohenry inductors, which is a lot of inductance compared to modern boards. Modern boards normally use like around 200 nanohenries typically. But funnily enough, ASUS for like Z490, was it Z490? Well, a lot of ASUS boards still use relatively high inductance inductors. At least they used to. I'm not sure about right now, but I think if you go back to, like, say, X99, X299, Z170, Z270, Z370, I don't think Z390, ASUS was using like 400 nanohenry inductors on their top of the line ROG boards. And then there's this thing, which, you know, like, it's a Haswell board, it's old, it shouldn't need a super high switching frequency. I figured this be on like 400, 600 nanohenry inductors. It's on 220s, which is really surprising, because the main reason that you'd want a low output inductance on your VRM is to improve transient response, which is kind of irrelevant when the integrated voltage regulator deals with that for you, right? So I find that really surprising. Like, this is a very low inductance motherboard by ASUS motherboard standards, especially for the time period. Yeah. Also, I think it's kind of like the little ASUS logo with the little gold plating. I think that looks kind of neat. It doesn't do anything. Like, don't get me wrong. It does absolutely nothing for the performance of the motherboard, but it does look kind of neat. The low inductance, however, that is really surprising. Because, well, I guess also it might improve the thing is, for a given size of inductor, a lower inductance will get you generally higher current handling capabilities. But again, like, it's a Haswell. It doesn't need a ton of current. So I was really surprised that these are 220 nanohenry inductors. But yeah, So that's kind of interesting because like later ASUS boards are 400 nanohenries, earlier ASUS boards are like 400 to 800 nanohenries, and then there's this thing 220, which yeah, would like I really didn't expect that. Like the Maximus 11 Gene, right? That's a Z390 board. That's on 400 nanohenry inductors. Weird. Anyway, um, for the output filtering, we have a rather interesting mix of capacitors. So all of these, so these and this one over here, those are all. Oh man, okay. This is kind of turning into a mess. These are 6.3 volt. Do I? I did not think this through. Okay, we're gonna put it over here. So these are. Is it Nichicon or no? It's Nichicon. Yeah. So these are Nichicon FP 10K capacitors. Aluminum polymers through holes, as in they have legs. And the reason I point out that they have legs is that the legs are bad for the equivalent series inductance, but again, not very relevant when you're on a Haswell CPU, but 10,000 hours rated at 105 degrees Celsius, which is basically as high a endurance rating as you can get for your aluminum polymer capacitors. And these are 6.3 volts and 560 microfarads, which is kind of like that's sort of the norm for motherboards to like high-end motherboards. Even now, use basically this. You have 10K rated capacitors, 6.3 volts, 560 microfarads, and they just kind of get slapped everywhere. And the reason why this spec of capacitor is used is because there's like a 5-volt rail, right? That you have, and so like you have 5, 6, like you have those same capacitors used over here for the input filtering of the memory VRM. You have them hanging around the PCIe slots for filtering things like the 3.3 volts as well as the 5 volts. Actually, the PCIe slot doesn't take 5 volts, but you know they're hanging like they're for filtering like the 3.3 volts down there. Then potentially 5 volts down here, or chipset power filtering over here. Like there's no harm in having a capacitor rated for very high voltage. And in terms of like ESR, your 6.3 volt capacitors will generally be able to have similar ESRs to your like 2.5 volt and 2 volt capacitors. So, you know, if you're a motherboard manufacturer, this doesn't really make a ton of sense to have a mix of like 2.5 volt and 6.3 volt capacitors on your motherboard. It makes a lot more sense to just slap 6.3 volt capacitors absolutely everywhere. Instead of having like a whole new capacitor SKU that you include in your production plans. Because the thing is, like, these capacitors are also used across multiple different motherboard designs, right? So, yeah, this is just kind of like we buy like 3 different kinds of polymer capacitor from Nichicon, and then we use them everywhere for everything. So that's why like you have 6.3 volt, 560 microfarad output filtering capacitors on a power rail that maxes out at like 3 volts. Right? Like they could have used 4-volt capacitors. They didn't because 4 volts is actually kind of an awkward capacitor rating. It's not very common. But anyway, so that's these 6 capacitors are 560 microfarad. But the wacky thing is that these right here are those, and man, I really didn't plan this out. So those are 100 microfarads, also FP10K, but 16 volts. And you might be looking at this like, why would you put 16 volt capacitors on the output? Again, it's the same reasoning as before. These 16 volt 100 microfarad capacitors get used elsewhere on the motherboard. Though on this motherboard specifically, the only places I found them is like, there's one down here, and I think there's one over here. And that's it. So this board actually is not a very, like this board isn't a very good example of these capacitors being reused for other parts of the motherboard, but I'm pretty sure I've seen these capacitors also used on like some ASUS GPUs and a bunch of other like motherboards from ASUS that aren't this one. This motherboard tends to use a lot more of the like the same caps that it uses for input filtering, but we'll get to those. Now, why would you put these 100 microfarad capacitors that are, you know, 16 volts on the output of your VCC in VRM? Like, how does this make any sense? You don't need 16 volt rated capacitors. Well, it's very simple. You don't, like, by putting more capacitors in parallel, you effectively get a lower ESR and ESL, and you don't necessarily want a super high output capacitance because it can make it, like, it basically the more output capacitance a VRM has, the more difficult it is to intentionally raise and lower the voltage. So if you're going between which actually for VCCN doesn't make any sense. I have no idea why these are 100 microfarads now that I say that. Like, there are motherboards where it's a real concern that if you have too much output capacitance, it gets kind of difficult to quickly slew the voltage up and down between like idle and full load. But this outputs a fixed voltage. Like, this output's basically a fixed voltage. I have no idea why they put 100 microfarad capacitors on this. Yeah, I have no idea. As for why they're 16 volts, that's a convenience thing. Like, they already have a bunch of these 100 microfarad 16 volt capacitors. But yeah, so for some reason, they didn't want a bunch of extra capacitance. The reason I don't get why they bothered with these 100 microfarad caps is, like, I'm pretty sure if they just put 2 more of these on the output of the VCCN and just didn't have these at all, it would have performed like the same, probably. Yeah, I'm pretty sure that would actually have like roughly the same performance because, like, technically speaking, more capacitors in parallel, less capacitance, but more capacitors in parallel gives you better ESL, better ESR, and so you get better voltage regulation. But this is VCCN. Like, it doesn't matter. So, yeah, this VRM is like really fancy considering what it's trying to power, which is a Haswell CPU, which is, yeah, I'm very, very, like, it's not a bad thing. I'm surprised they bothered. I'm very surprised that they bothered to do that. But speaking of things that I'm surprised that they bothered to do, the input filter on this thing is ridiculous. Seriously, look at it. These are the bulk input filtering capacitors. Right? This is 6 270 microfarad, 16 volt FP10K caps from Nichicon again, right? This spec, this is normal. What's not normal is why there's 6 of them. There are modern high-end motherboards where you'll have actually no, not high-end ones, but actually I think the Z690 Unify X has literally 4 bulk capacitors for input filtering. 4. And they're not higher capacitance. They're not tantalums. They're not SMD or anything. They're, and like, to be fair, ASUS has had like massive input filtering capacitor setups for a very long time now. This is kind of the norm. Like, I'm not surprised. Like, it's an ASUS motherboard. There's a bunch of input filtering capacitance, way more than I'm used to seeing on most other manufacturers' boards. I'm not surprised, but like, why on a Haswell board? Anyway, yeah, so, like, speaking of unnecessary things, all of this input filtering. Like, I'm pretty sure there are X79 boards that have less input filtering than this does, or similar amounts of input filtering. So, yeah, this is just an ASUS, like, this VRM is really, really like, it's not overbuilt. Well, no, it is overbuilt. Like, the way more current handling capacity than absolutely necessary. Like, the thing is, like, compared to modern motherboards, this is very tame. But yeah, compared to what it's actually powering, this is really, really, really overkill. Yeah. Cause like, like, looking at this compared to modern motherboards, But then you realize, wait a minute, this is powering a Haswell CPU. Why is there so much output filtering? Why did they bother with like 2 different types of output filtering capacitors? I'm pretty sure they didn't, like, I'm pretty sure you could remove half of these and it wouldn't make a difference. Why is there 6 input filtering capacitors? Honestly, like 2 or 3 of them would have probably been just fine. Yeah, like, very fancy VRM. As for the 8-pin power connector, that's just a standard folded pin 8-pin power connector. You don't need a fancy high current 8-pin power connector for a Haswell CPU. Like, this folded pin connector is still good for over 200 watts of power. I want to say it tops out at like slightly over 300, but I'm not 100% certain right now. Anyway, yeah, so the VCCN on this, very, very fancy considering that it just has to power a quad core with an integrated voltage regulator. Anyway, let's take a look at the memory power delivery, which was even more surprising in some ways. Yeah. Wait. Yeah, let's take a look. There's nothing really else to look at, right? It's a Haswell board. This is the only big VRM on the board other than the memory power delivery, unless you want to talk about the chipset. Um, but anyway, I don't want to talk about the chipset. Anyway, so memory power is handled by this right here. Oh, that's convenient. It's just a nice little rectangle. We've got some very cool dual NFETs. Cool in many ways. So these chips right here, oh, I guess I should start with the controller. So the controller is a ASP 1103, and if you've watched a lot of my PCB breakdowns and paid entirely too much attention to them, you should recognize this part number because ASUS loves this voltage controller, and they've been using, like, this is still used on like high-end DDR4 boards from ASUS because memory power delivery really isn't that difficult, so there's no reason to use anything else. Anyway, this is a 2+0 voltage controller, built-in drivers, so this thing connects directly to the dual NFETs that we have here. And speaking of the dual NFETs, I guess I shouldn't have split, well, I should have highlighted them as a separate chip is basically what I'm getting at. I shouldn't have highlighted them together. They're not, like, this is a two-phase VRM, so... Anyway, so we have the ASP 1103 running as a 2+0, and then down here we have some Texas Instruments again, CSD 87588Ns, and these are really fancy. Because as you might be looking at these, and those don't look like the same kind of packaging material that we have over here, and you'd be right about that because these are metal. Also, they're hot. Like the top of these is actually the switch node of the phase, so you really, really don't want to drop anything. Like these are like a short circuit hazard compared to these. Like. With these, you have, like, basically what you get on these pins over here. Actually, I'm not sure if I should highlight all of them. But basically what you'd be getting on this side of the inductor, like on the foot of the inductor over here and the output of this MOSFET over here. Yeah, I'm pretty sure that's the switch node. Yeah, you have that on the top of these. So, yeah, in that sense, they're a bit of a short circuit hazard. Not like more like a concern if you're doing LN2 overclocking, not a concern if you're on ambient, right? Like, I guess if you dropped a screw on one of these while the board was running, you would have a very bad day, but why are you dropping screws on your running motherboard, right? Please don't do that. Actually, like, speaking of short circuit hazards, technically speaking, every every single little solder joint you see everywhere is kind of technically a short circuit hazard. So these aren't really special in that sense. Don't drop screws on running motherboards, right? Simple. But it is something to keep in mind. Like, yeah, the casing of these is actually the switch node of the phase. These are 25 up to, I should again say up to 25 amp dual NFETs. And again, that just means there's a high side and a low side built into them, and the controller drives them directly. And outputting 14 amps of current to the memory at and this is 500 kilohertz. So basically the same operating parameters as here, except instead of 2 volts, we're talking. Wait, did I do it for 2 volts in the end? It wouldn't really make that much of a difference because I did it for 1.8 volts and 2 volts would probably have roughly the same heat output. Anyway, so assume like 1.8 volts output voltage. This would produce about 2.5 watts of heat. Which does mean this could potentially run kind of hot if you had like 4 memory sticks and a pretty heavy memory overclock, because this doesn't have a ton of surface area and it's right on the edge of the board. But also 14 amps is a lot of current for the memory and the memory controller to pull. So yeah, like I don't actually have hard numbers for how much power DDR3 pulls. I do have some numbers for DDR4, but I've never measured DDR3. So anyway, but yeah, like as long as there's some... The thing is, there's no real other heat generating components in the area, so actually it'll probably cool itself just fine. Right, with the main Vcore VRM, like you have a real concern of like the heat from the other phases affect like reducing the current handling capability, but here it's like, okay, so these are admittedly right next to each other, which probably as isn't exactly optimal thermally, but then it's like, well, there's nothing over here and there's kind of nothing over here. Like your 24-pin power connector really shouldn't be getting hot for any reason. Oh, I guess there is a linear actually, that might just be a switch. Nah, that's a switch. It says PQ. There's no way that's a linear regulator. Yeah. So, anyway, like, yeah, so this will cool itself just fine. And also the metal casing helps with the, ability of these to dissipate heat somewhat. Now, what I found really surprising about the memory VRM is how much output capacitance it has, because these 5 capacitors are all memory, and so are these 2. So in total, the memory VRM has 7 560 microfarad 6.3 volt capacitors for output filtering, which is like a lot. I really didn't expect to see that much, but yeah. And so that's the memory power delivery. And let's talk about the actual memory topology, which is far more important for memory overclocking capabilities. Well, actually, on DDR3, it's not as important, but affects memory overclocking far more than the actual power delivery usually does, because RAM is really not that... Like, the RAM and the memory controller really aren't that difficult in terms of power delivery requirements compared to, say, the CPU, if the CPU wasn't a Haswell CPU. Anyway, let's take a look at the topology. And the topology on this board is a T topology. As you can see, we have a trace that, like snakes its way in over here, and then it splits and sends one branch that way, and then the other branch goes this way. And, you can see that it hits the same pin for each of the DIMM slots, and this is a T topology layout. And you can also see the same kind of thing going over here, and over here, right, where you have splits like that. Whereas in a daisy chain topology, instead of doing what we see here, you'd see something like bam and then bam, right? And now with DDR3, T topology was a very, very popular memory topology, and the reasoning for this is very simple. DDR3 doesn't clock super high. Also, a lot of people wanted DDR3 is relatively limited in terms of how much capacity you can get per memory stick. And so if somebody wanted to run, say, 32 gigs of memory on their DDR3 system, like, they were kind of restricted to using 4 memory sticks with many, many memory ranks, because I don't think you can get 8 gigabit DDR3 memory chips. So with 4 gigabit DDR3 memory chips, if you want 32 gigs of memory, you have to have 4 ranks of memory on each memory channel, which basically means that T topology was, very popular because it allowed those very high densities to work well, because the benefit of a T topology layout is that the electrical distance from the memory controller to each of the memory sticks is the same. That's why we have this whole weird branching thing going on. The downside to the T topology is if you only have one memory stick, you have a great big piece of unterminated wire hanging off of your memory trace, which is terrible for high-speed signaling. But DDR3 doesn't run that fast, so it's not really a concern. And so with DDR3, T topology layouts were very, very popular. Also, this is a 6-layer PCB as far as I can tell. So yeah, and T-top. So the funny thing with DDR3 T topology is where on a DDR4 motherboard with T topology, there's a big difference between having only one DIMM slot populated and having both DIMM slots populated. With DDR3, you can potentially hit the exact same speed with 4 sticks as with 4 sticks on a motherboard as with 2 sticks. So that's kind of the reason why T topology was very popular at the end of the DDR3 era. Though, funnily enough, for early DDR3, daisy chain was the typical memory topology because it was easier to lay out, I guess, and maybe the memory control, like I guess like very high rank count memory setups weren't that common, or the memory controllers just didn't really want it, like didn't had a hard time dealing with T topology. Anyway, yeah, but for like the higher the memory speeds are, the less viable T topology is. Like, fun fact, memory sticks used to be internally T topology. Like DDR2 had a T topology command address bus, if I remember correctly. Or yeah, well, remember correct. Yeah, technically remember correctly. The one issue there is like I'm not really much of a DDR2 person. So for me, DDR2 information is more just in passing. But yeah, if I'm not mistaken, DDR2 was literally T topology on the physical memory sticks themselves. DDR3 actually adopted a like flyby command address bus topology, which is basically kind of like a daisy chain. And yeah, but as memory speeds keep going up, the like complexity of the topologies keeps going down, because fancy things like this don't cause issues at low speeds, but at high speeds, the reflections that the unterminated trace can potentially cause, and just other issues it can lead to, it's just better if you don't do this. So yeah. Anyway, the one other thing I wanted to kind of point out about this board, which I think is really neat, is that you can actually see the entire Vcore, like, well, yeah, you can basically see the entire Vcore power plane on the back side of the board. I mean, you can't really see it that well in this photo, and also we have some linear regulators hanging off of the VCCN down here. I don't know what they're for. But yeah, you can basically see the power plane actually going all the way to the CPU socket, which is really like with modern motherboards, you'll generally only be able to see a power plane that like goes all the way from the VRM to the socket like this on boards that are like 8 layers or more, because on say a 6-layer board, typically this area of the PCB is actually dedicated to a bunch of IO signals. Especially on like Ryzen, you'll have just a bunch of traces running through this area for things like your PCIe and stuff. Yeah, but this, being a like older motherboard with, I guess technically less IO connectivity, we do get a power plane that just kind of goes all the way to the CPU socket, which is kind of neat to look at. Not that, I guess technically it's beneficial, but again, it's a Haswell CPU, so like, who cares? Anyway, yeah, that's the Maximus 7 gene. Damn, this took way longer than it should have. Anyway, I had a fun time talking about this board. This thing's really, really excessive for a Haswell CPU. Like, like the voltage. Also, I guess I could have pointed out that ASUS likes to tack on these extra multi-layer ceramics outside the socket, which are arguably more effective for power filtering than the ceramics you have on the back of the socket, just because they're on the same layer as where the socket actually solders to. But yeah, so that's the Maximus 7 gene. It's kind of like I enjoyed looking at old boards like this. They were just so much more interesting. Like today, it's always the same thing. It's like here you have a high phase count controller, many high current power stages. 6 layers, daisy chain. Everything is daisy chain now, unless it's 1 DIMM per channel. To be fair, I'm not saying I want T topology to come back, because like imagine trying to run 2 sticks of DDR5 on a T topology. It probably wouldn't work. It would be like running 4 sticks of DDR5 on a daisy. Actually, the funny thing is, some daisy chain DDR5 boards can actually handle 4 sticks just fine, or at least okay. But because the main problem with a daisy chain topology and 4 memory sticks is matching up the timings of the signals to where the memory sticks are relative to the memory controller. The main problem with a T topology is that it just puts more load on the memory controller, which is like, it's fine if your signals are slow. It's not fine if your signals are very fast. Anyway, Yeah, I'll end the video here. So I guess thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, the usual YouTuber merch. And I also have a Bandcamp. There's a link to that down in the description below as well. And that's it for the video. So thanks for watching and goodbye.